Today from Australia, I'm John Broughton, and my subject is the computation of asteroid dimensions from integrated occultation data. The observation of asteroid occultations requires coordination, preparation, and a great deal of luck to achieve the outcome we strive for in fitting a well-constrained ellipse to the observations. But all too often circumstances conspire to limit the proceeds to just a single chord, or several off-centre chords from which dimensions cannot be measured by conventional means. When occultations are categorised accordingly, no less than 82% fall into that second category, lacking conclusive results. And it's no wonder, given all the factors required to succeed. Observers can count themselves lucky to see an occultation, given the uncertain path of the shadow, and lucky to avoid being clouded out. Hopefully the telescope has been pointed in the right direction, and technical faults don't crop up. Ultimately, a successful campaign depends on positive results observed from 3 sites spread over at least half the path width. Given the reality that most events don't give definitive results individually, I've sought to develop procedures to combine them. The first principle is to represent each occultation by an event diameter, because that provides various viewpoints from which to calculate a mean diameter and ellipsoid dimensions. The more viewpoints we have, the better the accuracy. Here's a schematic diagram displaying 5 events for a hypothetical asteroid with timings represented at left. The first step is to convert the timings to chord lengths measured in kilometres, and to fit ellipses to the chords whenever possible. Event diameters for Category 1 events arise by a straightforward conversion of ellipses to circles of the same area. These event diameters, being the most accurate type, are double weighted in subsequent calculations. Event diameters for Category 2 arise directly from chord lengths multiplied by a constant representing the relationship between mean chord length and mean diameter, as derived from simulations involving a variety of shapes viewed from random directions. Incidentally, chord length measurements are immune from time-based errors, such as the shift affecting the uppermost chord of this Pallas occultation from 2011. The resulting event diameters are given unit weight or less, depending on the length of the chord. This diagram illustrates how weight is measured. The chord length in red is fitted to a circle representing the mean diameter. If the chord lies in the grey area outside half the radius, it is deemed to be a short chord, and given reduced weight according to its length in the hexagonal shaped diagram. This ensures that short chords and blinks have little detrimental effect on mean diameter results. Notice that the third event started with 2 chords that were combined to make a single chord length. The same weight rule also applies at that earlier stage. Now the weighted event diameters can be combined to derive the mean diameter. Because of the interrelationship between weights and mean diameter, the whole procedure is cycled several times to arrive at a final result. The combined uncertainty for this number of events is likely to be in the 3 to 5% range, as derived from chord simulations and from ellipse uncertainties extracted from occult. Geometric albedo is then derived from mean diameter and absolute magnitude. The major axis of the asteroid derives from the longest chord length from the first 3 events or the longest fitted ellipse, whichever is greater. The minor axis comes from the narrowest ellipse. The third axis can then be calculated from the major axis, the minor axis, and the mean diameter. The resulting tables of asteroids with measurable dimensions are growing month by month. One Category 1 occultation, or at least 3 of Category 2, are required to qualify for inclusion in the list of preliminary dimensions. The mean diameter sigma is in the 5 to 15% range at this stage. Once the second Category 1 occultation has been observed, the asteroid is promoted to Stage 2, which now exceeds 100 entries. The mean diameter sigma for those is better than 5%. See the IOTA Worldwide Observations webpage for a link to these lists. Here are results for all 7 main belt asteroids with derived mean diameters larger than 300 kilometers. Observable occultations by Ceres and Vesta are rare due to their brightness, and both have yet to progress beyond Stage 1. However, Ceres is the most differentiated body in the main belt, and probably unique in having a once liquid icy mantle that, due to gravitational equilibrium, conforms closely to the shape of an oblate spheroid. Therefore, a well-observed 1984 occultation alone is sufficient to measure a mean diameter within 1% of the currently accepted value derived from HST images. It's smaller by 8 kilometers, but there's a chance that discrepancy could be resolved soon, depending on the results of an event visible from the eastern United States on October 25. Bear in mind this is the last occultation by Ceres with potential to provide dimensions at the kilometre scale prior to the arrival of the Dawn spacecraft in February 2015. Vesta's mean diameter is known from the Dawn mission to be 525 kilometres. The occultation diameter differs from this by 4% after just 5 occultations. Of the others, Pallas has the most observations, with 15 events seen over the past half-century. When the mean diameter is calculated after each event, the 1 sigma uncertainty improves from 18% in 1961 to just 3% by 2011. The biggest improvements in accuracy occur after each Category 1 occultation, as denoted by the asterisks. The latest figure for interamnia is even more accurate by virtue of 2 recent Category 1 occultations, bringing the total to 5. Europa's mean diameter has settled into a remarkably small range of variations over the past 8 events. Having quite accurate diameters for 100 asteroids enables geometric albedo values to be averaged according to taxonomic class, except for the 2 rare classes at top that I've included for completeness. Due for launch later this year by the European Space Agency is the Gaia Astrometry satellite. This observatory will be capable of measuring star positions to an extraordinary degree of accuracy, equivalent to the width of a house and the distance of an asteroid. Asteroid positions will be measured at lower accuracy due to their asymmetric shapes. When catalogues become available later this decade, the outcome will be path predictions with 1 kilometre accuracy for tens of thousands of asteroids. The high probability of seeing many occultations will enable current observers to be far more productive and potentially attract hordes of new recruits to the field, leading to a rapid expansion in the list of asteroid dimensions. The new astrometry could be the launching pad for novel techniques in fitting complex shapes to the observations. In this concept diagram, the observer is at top, asteroid at centre, and star at bottom. The position of the asteroid on the sky will be known to kilometre accuracy, as will the relative position of light rays the observer sees being occulted, as long as the timing is accurate. Now let's add a second line representing reappearance. Thus we have two lines in the direction of the star instead of one transverse chord. If the pole direction and rotation period are known quantities as well, then these lines could be transformed into asteroid-centric coordinates. Lines from all events will then enclose a void into which a shape model could be formed. Like this, but with scores of lines and calculated in 3 dimensions. A decade from now, main belt asteroid and Jupiter-Trojan occultations will be considered run-of-the-mill observations, and the new frontier will be out in the Kuiper belt, where planetoids abound in large numbers. The objects discovered so far barely scratch the surface of what is out there, and the existing astrometry, in most cases, falls woefully short of what is required to generate useful predictions, with current path uncertainties often on the order of 10,000 kilometres. Within range of detection by Gaia are about 15 of the largest known Kuiper belt and scattered disk objects. Their positions will be measured 70 times during the mission. Consequently, any occultation predictions stemming from that will have high probability paths, but rarely will there be events within the range of small telescopes from such a small number of slow-moving objects. However, there's a revolution in the making. By 2022, the Large Synoptic Survey Telescope, or LSST for short, will become operational. With a 3-degree field and capacity to survey the sky twice weekly to the 25th magnitude, distant planetoids larger than 100 kilometres will be discovered in their thousands, literally overnight. After calculating the number of potential occultations these should produce, I came to an astounding conclusion. Events brighter than the 14th magnitude are 8 times more common than their main belt counterparts. To give a breakdown, there are estimated to be at least 70,000 objects of that size in the Kuiper belt, compared to just 200 in the main belt. That number drops to 50,000, or 250 for every main belt asteroid, if in all likelihood discoveries are not possible in crowded star fields. Those excluded fields also contain a lot of stars for which there will be no TNO predictions for many years. This reduces the ratio of potential occultations to 125. Finally, in allowing for a 16 times lower rate of apparent motion compared to main belt asteroids, the ratio ends up at 8 to 1. That amounts to 120 events occurring somewhere on Earth each day. So many, in fact, that one is likely to be crossing the globe even as I speak. On average, a fixed observer will be within trans-Neptunian occultation paths 100 times over the course of a year, and potentially see one in an average week, after allowing for 50% being clouded out. These events will have a path uncertainty around 300 kilometres by the end of the first opposition, improving to 100 kilometres after several years. By 2025, stage 1 dimensions derived from occultations could well be dominated at the large end of the scale by trans-Neptunian objects. Photometric and spectroscopic observations of these distant planetoids would be extremely challenging even for 8-metre class telescopes equipped with adaptive optics. But given the great potential to record occultations for thousands of such bodies with modest equipment, the research on shapes and dimensions is destined to remain largely the domain of amateur groups for many years to come.